tire deformation is actually one of the major giblet twisters in car aerodynamics. In fact, for quite a long time, the impact that tire deformation had on a car's aerodynamics was heavily disputed, but we now know that it is a big deal. And to give you an idea about the different ways a tire can deform, well, in figure 3 here we have an example, and when you see a tire just hanging up and not on anything, there's no load on it. Then when you put it on a car and lower it, the weight of the car now pushes down, and particularly at the contact patch between the tire and the ground. Then the tire bulges out, as shown here in figure 3 with these different lines. And the region where this contact is made is aptly named the contact patch. And in figure 3, we can see some of the numbers about how much the width of the tire changes and also the height of the car then. So over maybe a few millimeters in the width and over a centimeter in the height. So the ride height of the car does change too. But tires deform in more ways than that. So for example, if you see a cold tire, it might have be deformed a certain amount, but once you heat it up, for example, by driving on it or by lighting it on fire, the rubber becomes softer, and that again changes how much deflection you get. And while no paper comes to mind about the mathematical function describing the contours of the tire, I'm willing to bet $100 that the temperature also affects exactly how the contours contour. And on top of that, each tire type is slightly different. They might be wider, have a greater diameter, have different tread patterns, and have different wall thicknesses, and so on. They all change the different tire deformations, so they might make the tire deform more or less, or in different ways, in different contours. Then the actual construction of the tire, so the various layers and the compounds used in these layers change the stiffness and again the deformation. Then again, something that I can't remember seeing a paper on, but I'm willing to bet that the wear of the tire also affects the deformation, because that again changes the stiffness of the tire. Then on top of that, when you spin the tire, you actually fling rubber down into the ground, and as the tire rotates back up from the ground, the rubber stretches out. And this was actually one of the first things I remember learning about tire deformation, and I remember being mind blown because I'd never thought about that. And the guy who was telling me about that didn't seem to be joking, so I'm pretty sure he wasn't teaching me on purpose. He wasn't teaching me wrong on purpose. It was actually real, and it is true. Anyway, all of this is to say that tire deformation is very complex, and it deforms in more ways than we're even aware of even now, and that changes the overall geometry of the tire and the car. So in figure 3, we see 3 different lines, the red, blue, and dark blue. And you can see that for some of them, the contact patch is wider and the curve around the sides is different. So the contact patch is down at the bottom here. So to see how different tire deformations affect a car's aerodynamics, we're looking at this paper called, if we scroll up here, Numerical Investigation of the Influence of the Tire Deformation and Vehicle Ride Height on the Aerodynamics of Passenger Cars. And it is open access, so you can find it in the link below as usual, and the DOI of it is just down here at the end of the page. So tire deflection definitely affects the geometry of the tire and hence the aerodynamics around it, but it also affects the ride height, as I mentioned, and that's because as the tire gets more squished, the car will sink down more. Now, it isn't that much. We saw before it's maybe a centimeter or so, but it is something, and it highlights how the ride height might affect the car's aerodynamics too. So the authors wanted to know how changing the ride height changed the aerodynamics too. As such, in figure 4, if we come down here, they looked at plus and minus 30mm height changes from the default height for the car. And that's quite a bit. And before we even look at the results, I'm guessing that there will be a big difference. Perhaps the lift will be lower and the drag will be lower too. That's a common trend, but we'll have to see later what exactly happens. Now, one thing that I'm quite impressed in this paper is the number of different variables they looked at. So we just covered the tire deformations, then the height changes, and now in figure 2, if we scroll back up, they also looked at 2 different underbody types, smooth on the left and detailed on the right. Now, one of the driving reasons for looking at these 2 different types of underbodies is that for electric vehicles, an almost completely smooth underbody is common and becoming more and more common. While for the good old ICE engines, there is currently a few protuberances that come out in most cars, but I should mention that the underbodies these days are way smoother than they used to be even for ICEs. So if you go back to the 70s, for example, everything was completely exposed, so they're much better these days. And the reason why smooth is generally better is that nothing for the flow is there to get caught up on and separate. So you get a much nicer flow that reduces the lift and drag, hopefully. And we'll see later on how the smooth versus rough underbodies affect the drag. Now, while it's awesome that so many different details were considered in this paper, unfortunately that came at the expense of the quality of the simulations. So the CFD they used here, and it's nice that they use CFD because you get a plethora of information, but in figure 7, we see their domain. So if we come down here. So overall it looks good, except if you look closely, let's zoom in really closely. Here we go. You can see that the wall closest to us cuts through the center of the car. Then they have made a boundary condition here saying that it's a symmetric one, just there, a symmetry plane. So what that means is that they are only simulating half the car, in this case, the right half. The major reason why anyone would want to do that is to reduce the number of cells you need and hence the simulation time. The way you can get much more detailed flow is with this method, but it comes at the expense of having only half a car. So let's quickly discuss whether it's okay to do that, and if it is in this case, and when it isn't okay. So for streamlined objects like wings, the flow is generally symmetrical and steady, and hence you can simulate just half a wing and mirror it, and the amount of accuracy you lose isn't that much and could be worth it. On the other hand, when it comes to bluff bodies, which a car is, bluff bodies have very unsteady wakes, and that almost comes with always a asymmetric flow. So, and it's also unsteady. So only simulating half the car can come with errors. So let's just keep that in mind and look at the general trends instead of the exact numbers going forward. Anyway, for their CFD, I think they did a pretty decent job otherwise. They used OpenFOAM, which is a very powerful and free software for CFD, but hard to learn. So if you want to learn how to use it, you can to use on simulations like this and other things you want to do, then take our course in the link below, and we have a Christmas special on right now, which I think you'll really like. Anyway, interestingly, they went for the Delayed Detached Eddy Simulation approach, so DDES for short. And as we have covered in other podcast episodes, this version is definitely an improvement over the regular DES case, but it's arguably not as good as the IDDES case, which is often used for car simulations. Now, one major advantage of the simulation is that they used slick tires, which greatly simplifies the simulation setup. And honestly, even today, we have no real way of modeling a rotating tire with deformation and tread. The only real thing we have is the immersed boundary condition, which isn't available for all softwares. So having a slick tire means you don't need to worry about the tread or its effects. So that greatly improves the accuracy of the simulation and also reduces the number of cells you need, etc. So they also used a closed rim, which again greatly simplifies the simulation setup because you don't need to have all these spokes and take them into account in terms of the rotation. The authors also are pretty smart because they say that they didn't want to add the tread or open rims because they wanted to isolate the deflection effects for effectively this baseline tire and rim combo. So there's definitely merit to that idea. It's much easier to use a slick tire with a closed rim approach as the baseline and then work up from there instead of going all out to begin with and then trying to work down with less complexity. And also each tire has very different treads, so it's kind of like, where do you start? So it's a good idea to start with a smooth tire here. Now, the tests are done at 38.88888888889 meters per second, which might seem like an odd number, but it equals 140 kilometers per hour, which is the velocity that certification is done for cars. So if you ever see this number, then that's why it was chosen. Now, one thing that I wonder after looking at figure 7, if we come down here, is how well this domain reflects the domain that was used in the wind tunnel to get the validation data. Because while this is a big domain, and when you go into wind tunnels, you try to reduce the blockage ratio as much as you can. So in other words, you try to make the frontal area of the vehicle only occupy maybe a few % of the cross-sectional area of the test section. And the reality is, though, that there are still minor effects that can occur from having the car so close to the wall. And that can be the difference between getting CFD results very close to the wind tunnel data and not. So for anyone listening, when you do CFD, try to use a domain that is, at the very least, similar to the wind tunnel test section that you're using to test your car in for validation data. It might seem like a real pain, but when you're setting up your CFD, you really want to get this be as close as possible because it will make things much easier later on when you want to validate your results. Now, they have done something interesting for the surface mesh for the general car. They say that they have a surface resolution up to 4 millimeters, which gives a Y plus between 30 and 100. But for the wheels, they refine it more up to 2 millimeter surface meshes, which gives a Y plus value of less than 10. So why would you do that? Well, first of all, a more refined mesh will generally give better results, but in terms of the Y plus, this is an important point. So the Y plus value you should have greatly depends on the turbulence model you use. And now we run into a potential issue. So these researchers used the Spalart-Almaras turbulence model, which is fantastic and a quick one for airfoils. It's only a one equation turbulence model, so it's a bit quicker. But in its original form, it is only really suited to meshes where the Y plus value is around 1. Here, the Y plus value is more than that, and quite a bit more. Now, they say that they chose the Spalart-Almaras turbulence model because a couple of papers, references 11 and 12, say that this turbulence model is good for cars. And here's the issue. So in its original form, it definitely isn't. There are many other turbulence models that are better. However, in reference 11, the authors clearly conclude that none of the turbulence models they tested were completely accurate. Now, by completely accurate, these models got to within about a few percent consistently. So I think that the Spalart-Almaras turbulence model isn't that good to begin with. However, there's one possibility that would override that, and that is that if they're using OpenFOAM, they could change things. The reference 11 used star CCM+. So the important point to note is that if you're using OpenFOAM, they could definitely have augmented this model to make it more accurate. However, I can't see anything in this paper to suggest that. So I'm going to say that this turbulence model is only really good to within a few percent and is definitely not the best one anyway. And that is partly because it isn't that good for cars to begin with. It wasn't made for them, but also because the Y plus values are too high anyway. Again, this is assuming that no changes were made to the formulation of it in OpenFOAM. Let's move on from that now. So the authors say that the contact patch is a very difficult region to mesh because it is prone to low quality cells, and that is incredibly true. I mean, when you get here, you might get negative volume cells or highly skewed cells, and there's a good chance that the contact patch is where they'll be. So you can see as the wheel comes down, you have to put all these really tiny cells in these really high angularity regions. So trying to resolve this angle is difficult, and even making the cells very small here may not be sufficient either. In table 2, we see the boundary conditions of the domain, and most of them are quite obvious. 2 of them are very important though, so let's cover them. The first one is the ground, and they've made this a translating wall boundary condition, and this means that the ground is moving at the same velocity, ideally, as a free stream flow. Now, that's very important because if you have it stationary or as a no-slip condition, then a boundary layer will form on it. That then creates quite strong differences between what you get in real life and in a wind tunnel with moving belt systems, and then what you would get with your CFD. Now, the reason why they went for a translating wall boundary condition and not a slip one is because a slip one may not actually be what you get in real life. Let me give you a scenario. So say you have a slip boundary condition for the ground, and that's great. No boundary layer will form up on it. But what happens if some flow from the car then impacts the ground? Well, nothing, because having the general boundary layer here is not going to form because it's slip. There's no viscosity. But in real life, there's a difference because the flow from the car will not interact with the ground, and there will be some kind of viscous effect. So that's a clever nuance in this boundary condition that they have here. For the wheels, they have a rotating wall boundary condition, which means that they pretty much just told OpenFOAM, hey, add a rotating wall, a rotating velocity to the entire wheel in this direction at this rotational velocity. And because this tire is slick with a closed rim, this boundary condition is pretty good. Another important point for all those out there looking to do simulations on cars, and really any simulation, is that in figure 9 here, this shows the time history first of the drag coefficient. And what that means is how this value changed with time through the simulation. So this time seconds is real time, so 4 seconds of real time of travel with the car. And for the first second, the results are all over the place. That is simply because the simulation is converging still, and this is an important point because even though residuals like the pressure or continuity have converged, that doesn't mean that other residuals like the drag coefficient has. The reason for that is because the flow is still developing, and one very simple way to see that for yourself is to simulate an unsteady simulation of a cylinder, for example. Then what you'll see is that it takes a little while for the von Karman street to form. So even though the residuals have converged, the actual formation of this flow physics pattern hasn't formed yet. So in this simulation, the researchers waited until the drag coefficient stabilized to within a certain level and then took an average, which is the correct way of doing it. Now in table 3, we see the validation of one of the cars they tested, something called the Driv model. And just a quick note on the Driv model. This model was designed as effectively a baseline car that anyone can download for free and simulate. It was made by the University of Munich, and if you want to download it, just literally go to their website and you do that for free. Anyway, they have the validation data for their smooth underbody and for the detailed underbody, and that is really cool. It's rare to see both. Now, one thing I want to point out is that the validation data comes from reference 14. And in that reference, the wind tunnel test section doesn't seem to match the CFD domain they have here in terms of size. So any differences we get in table 3 might be, at least in part, because of the differences in the test section domains, and not necessarily the other CFD settings. Anyway, the smooth underbody drag coefficient was very close to the wind tunnel results, just 28 counts different, and a bit higher, 28 counts higher, and that works out to be just 1.1% different, which is impressive. For the detailed underbody, the results were a little worse, 116 counts higher, which is 4.1% off. That could be due to a number of reasons. For example, it's only half a domain that they're simulating, or the domain size, or even the resolution of the mesh in the underbody wasn't good enough. But it's still pretty good. Up to 5% uncertainty is enough to look at quite a lot. Now in table 4, they tested another car called the Aero SUV, which you can see in figure 1, if we scroll all the way up here, is to the right in this figure. Not that one. Not that one either. Not that one. This one. Here we go. So the right one here is the Aero SUV. The left one is the notchback Driv. The Driv comes with 2 other configurations as well. We can get like a hatchback and one other one. Anyway, this is an SUV, which means that its wake is going to be much worse, and actually the nuances in the flow attachment over the rear are not as important here because you're going to be getting flow separation at the rear no matter what. Now, one thing that is interesting is that for this Aero SUV, they have validation data from reference 5 in terms of their experimental data and CFD data that they did in reference 15. So that's interesting. You not only get what those authors found in terms of their experiments and CFD, but now what these authors found with their CFD. Anyway, for this study, the drag coefficient was 156 counts higher than the experimental data, which is about a 5% difference. But comparing this CFD with the CFD results from reference 15, this drag coefficient is 74 counts lower, so a 2.3% drop. So overall, I think that either car is accurate to about 5%. So let's move on to the results now. So first, the authors looked at the effect of the ride height on the aerodynamics. In figure 10, we see the effects of the ride height on the drag area for the Driv car in the left plot and the Aero SUV in the right plot. So there are a few things to note here. The first is that the x-axis is for the different heights. So M3 is the entry car, it's been lowered from the baseline. B is the regular car height, so the baseline, and P3 is when the car is lifted. I'm not sure why they had to use such cryptic names. As a general rule, if the names aren't obvious to the reader at first glance, then they're not good names and should be different. Anyway, the drag area is plotted, and there's actually a very important value. This is a very important value for the automotive industry. The reason why is because, sure, the drag coefficient is super important, but if you have a semi-trailer with a ridiculously low drag coefficient of 0.1, let's say, well, that doesn't necessarily mean that it will have a lower drag while traveling at the same velocity as like a Mini, where the drag coefficient might be 0.3, but the frontal area is way lower. So as such, when comparing cars, the drag area is actually a very useful tool and really normalizes each car against each other in the real world. So that is why the y-axis is in the drag area, and note that it is still a delta, so a difference between the baseline and what we're seeing here in terms of whatever we're testing. What's more, we have 2 different types of bars here. One is for the smooth underbody, the black bar, and then the other one is for the detailed underbody, the hashed bar. and the authors wanted to see how the underbody roughness affect their results. Also, this is for the regular tire, as we can see in figure 3, from what I can tell at least. So there's no deformation at all, it's just a regular tire. Neither has the deformation or the change in height from the deformation being factored in. It's literally just the car being moved up and down by 30 millimeters. So for the Driv Air model, if we scroll back down here to figure 10, I think it was. Yep, here we go. So for the Driv Air model, a very prominent trend is that the drag area increases with increasing ride height, and that is true regardless of the underbody roughness as well. So that trend is very robust, and in fact, it is so robust that it is also true for the Aero SUV in the right plot too. Now the difference between these two cars is how much the drag area increases with increasing ride height. The Aero SUV seems to be a little more sensitive, and I think that that's because it's actually more a function of the frontal area than necessarily the drag coefficient. Maybe they both work together, but what I mean is that the Aero SUV has a larger frontal area. It's an SUV. So let's say you have a 2 count change in the drag coefficient for both of them, but not the drag area, just the drag coefficient. Well, if one car has a frontal area of 2 square meters and the other car has a frontal area of 3 square meters, well, the drag area changes will now be 4 counts and 6 counts respectively, literally just because of the drag area, just because of the area changes. So even though the drag coefficient changes were exactly the same, 2 counts, the differences in areas create a larger change. So I think for the Aero SUV, that the area is probably one of the driving factors behind these larger changes that we're seeing compared to the Driv Air model. Another thing to note is that the smooth underbody lowered the drag area, but it wasn't by that much, only like 7 counts. So that's not a lot considering how much of a change in the geometry there is. And this was for the regular tire. What about when we have some level of deformation? Well, in figure 11, we see what happens when you lower the car and add in tire deformation. And again, the lowering or the changing in the ride height isn't coming from the tire deformation, it's just artificial. And then the tire is being deformed and the change in the ride height because of that is being ignored right now. We'll see later on what happens when we do factor that in. So the ride heights are again those cryptic M3, B, and P3 labels. Now the tire was deformed to D2 in figure 3. So the D2 pattern is the purpley red line, so it's deformed quite a lot. So let's describe figure 11 because it is a little different to figure 10. So I'm finding the description a little hard to understand, but from what I can tell for the left figure, as I mentioned, I'm pretty sure it's just a standard ride height change and the deformation of the tire isn't being taken into account. For the right figure, we are now factoring in the additional change in ride height because of the deformation of the tires, from what I can tell. So for both figures, the tires are deformed into the D2 configuration, so the most deformed. For the left figure, the additional ride height change for the car isn't factored in. One thing to note is that for both cars, they experience very similar trends in the drag area. And that is a little surprising because, again, I imagine that the Aero SUV has a larger frontal area. Anyway, what these plots both show is that with deformed tires, you still get the same trends of increasing drag area with increasing ride height. Those changes we're seeing are now like between 2 counts and 10 counts. Let's now move on to the reason why we see these changes. So in figure 12, we see the frontal pressure, so the total pressure coefficient plots for these 3 different ride heights behind the car. This is for the Driv Air. And if you don't know what the total pressure coefficient is, then check out our YouTube channel. We have a video on there called Aero Fundamentals number 33, Total Pressure Coefficient Explained. And in that, we go through the math behind what it is and what it really means. And in a nutshell, it's akin to the drag. It's not the exact same thing, but it's very similar. Anyway, lower values, so blue values, are generally bad and red values are generally good. From these plots, I think one major advantage of the lowered ride heights is going from P3 to M3, is that the blue region gets a little bit smaller, so the drag drops. And one easy way to tell that is if you look at the wheel regions, you can see that as you increase the ride height, you still get pretty much the same width of the blue sections around the wheels, but now they're covering more height. So that is going to be more drag there. So the ride height is definitely affecting the wake and total pressure coefficient too. In figure 13, we see the effects of the underbody details on the normalized velocity, and this means that it's the local velocity divided by the free stream velocity, and it ranges from here minus 0.2 to 1.4. Now, one thing that really stands out to me is that the rear wheel wakes for the smooth underbody curve in more than for the detailed underbody. And I think that there might be a couple reasons for that. The first is that the detailed underbody features actually, they guide the flow, and they're literally physical barriers stopping the flow from meandering around wherever they want to. So I think that straightens the flow more. The other reason that I don't actually know if that's true or not, but possibly, is that because the underbody is smooth, the car's diffuser is potentially more effective now. The reason why I say that is because you have fast moving flow hitting the diffuser, so the diffuser has more energy to work with. So that should drop the pressure and perhaps suck the flow from the rear wheels in more. Again, I'm not completely sure if that is happening, but I think it might be. Now, in equation 7, the authors come up with another very intuitive reason as to why lowering the car reduces the drag area. So in effect, the more you lower the car, the more the front wheels are covered, and that is a major benefit because wheels are massive drag producers. So covering them with a much more streamlined shell, the car, will definitely reduce the drag area. So by covering them as well, you're lowering the frontal area of the car will reduce too, because the actual car's frontal area may not change, but is less because the frontal area from the wheels is lower too. So you will get a reduction there too. So that all makes sense. Now, we get to a pretty cool section next up. The authors are now looking at how the underbody's interaction with the ground is affected by the ride height. And one thing that they give is a skin friction drag coefficient, so this CF value here. And in figure 15, if we zoom out a little bit, we can see the skin friction drag coefficient over the Driv Aero model with a smooth underbody. And going from top to bottom, the car gets higher and higher off the ground. And around the front wheels, which is to the left of the plots, you can really see how as the car gets higher off the ground, the color becomes redder and redder. That means that the skin friction drag coefficient drops, and that makes a lot of sense because the more lower you get to the ground, the more a Venturi effect is created as you shove air through a smaller area. So as such, the speed should increase, and that means that the pressure should drop. So simply from this figure and general knowledge about fluid mechanics, you should be able to conclude pretty safely that the downforce from the frontal region should also increase. And interestingly, over the diffuser, so the right side of the figure, the skin friction drag increases with increasing ride height, going from M3 to P3 down the page. These changes are quite minor though, so I'm not sure if that's within the error of the simulation though. As a side note, something I always find incredible is if you look at all the blue regions on the car, that indicates negative skin friction drag. So that here you're actually producing thrust from the skin friction. That's pretty cool. Now in figures 17 and 18, if we zoom in a little bit here we go. So the differences in skin friction drag coefficients are seen over the smooth body and the detailed underbodies of the Aero SUV respectively. Incredibly, the detailed underbody features way more blue regions, so it's arguably better for skin friction drag here. I mean, you still need to calculate what it is quantitatively, but qualitatively it looks better. Now in figure 19, we get a great breakdown of the drag areas of the various parts of the car for the Driv Air model, and the differences between the smooth and detailed underbodies, going from solid to the hashed column bars, and for different ride heights too. So M3, B, and P3, so going from minus 30 to 0 to plus 30 millimeter height changes. So the standout trend here is that regardless of the ride height, the detailed underbody produces more drag area, but it's not that much, like 6 counts, and that is not necessarily outside the error of the simulation. Another trend to see is that regardless of the ride height, the breakdown of the drag area for each component stays the same relative to each other. So for example, the underbody obviously produces the most drag area, but the front tires are second, followed by the rear tires, and then the front rims, and then the rear rims. As a side note, the rear rims are almost nothing here, like this cyan color is very small. And they also have the same breakdown, but for the Aero SUV in figure 20. And now, interestingly, for the smooth underbody, the drag area isn't that much more than the other components, and even to the point where for the baseline and P3 ride heights, so these two right ones, the rear tires actually produce more drag area. So these blue columns for the smooth underbody. So it seems like for the sedans, I guess I shouldn't say all sedans, but because this is just one configuration, but for perhaps sedans, the underbody plays a far greater role in the drag area than for the SUVs. That is, the underbody, let's now look at the tire deformation effects. Now in figure 21, we see the difference in contact patch areas for these different deformations, and while the deformation didn't seem all that much, the contact patch areas changed quite a lot, like close to double, I would say, going from the baseline to the D2 contact patch. Now in figure 22, we see the changes in the drag area for the different tire deformations, B, D1, and D2, for the smooth and detailed underbodies, for the Drive Air and SUV left and right, respectively. Now, remember that the D2 configuration is more deformed than the D1 configuration, as we see in, where was it? Here we go, figure 3 here. Now, for both cars, if we scroll back down to figure 22, I believe it was. Here we go, yep. For both cars, the more the tire is deformed, the more drag area is produced. And in fact, the amount it increases is pretty constant between the smooth and detailed underbodies. Now in figure 23, we get the familiar breakdown of the drag area for the various car components, but there is a difference in the trends between the Drive Air on the left and the Aero SUV on the right. For the Drive Air car, increasing the underbody area, we see increased underbody drag area for the rear tires and for the front rims as well. For the Aero SUV version, the underbody wasn't really affected. The drag area is pretty much constant regardless of the deformation of the tires, but both the front and rear tire drag areas have increased. So the general trend is that for the sedan, the rear tires, front rims, along with the underbody, contributed to the increased drag with increasing deformation, while for the Aero SUV, it pretty much just is the tires. The underbody and the rims don't seem to make much of a difference in terms of drag area with changing deformation. And that might be a function because SUVs are usually higher off the ground too, so the wheels are more exposed. Anyway, in figure 24 and figure 25, if I zoom out a little bit, too much, there we go. We see the static pressure coefficients on the wheels around the Drive Air car, and honestly, there isn't much of a difference. Perhaps a little lower static pressure coefficient around the jetting vortex region for the baseline tire, so around here. But everything else looks pretty similar. Oh, and I should also mention that if you don't know what the static pressure is, the static pressure coefficient, then on our YouTube channel, we have another video called Aero Fundamentals number 12, Pressure Coefficient Explained. Now, the static pressure coefficient is different to the total pressure coefficient, so that video goes through the mathematics of it and what it means and how it's different. Now, in figure 26, we see the drag produced just behind the front wheel of the Drive Air car. Let's zoom in a bit. And it is very noticeable that on the inside of the wheels, so just around the underbody as well, as a tire deforms more and more, the drag increases. Now in figure 27, we have the same plane but for the Aero SUV, and we get a similar trend. But I think also the drag from the jetting vortex, which is on the outside of the wheel, also increases a little bit, because if you look at the outside of the wheel, the drag produced seems to increase a bit more as you increase the deformation more and more. So perhaps this deformation is producing stronger jetting vortices, and that makes a lot of sense because you have a larger frontal area down close to the road, so more air has to be redirected around, and that rolls up around the contact patch into the jetting vortices around the bulge. Now in figure 28, we see the normalized velocity, zoom out a little bit, here we go. We see the normalized velocity in the plane going through the tires for the Drive Air car, and as the tires deform more and more, the wake of the front wheels get larger and larger, so as we go down the page, you can see how much more large it gets as you go downstream. Then that impacts directly the rear wheels. So the rear wheel's wake becomes unaffected though, from what I can tell. Like, even though you have a bigger wake hitting it, the rear wheel's wake is not really that much different from what I can tell. Maybe it's a little bit less blue. Anyway, We've now covered the effects of different ride heights and different deformations. What about when you combine the two? So in figure 29, here, we see the effect of the different tire deformations with the change in ride height it induces for the entire car. So it's really a very realistic effect where you deform the tires, the entire car will sink down as well by that 6.5 millimeter or 13 millimeter amount. And for the Driv Air model, it's 6.5 millimeters for the D1 and 13 millimeters for the D2 deformations respectively. And for the Aero SUV, the D1 is 7.5 millimeters and the D2 is 15 millimeters, so it's a bit more. But anyway, we see a really interesting turn of events because as you deform the tires more and more, the car gets lower to the ground and that reduces the drag area. But we also saw that deforming the tires also increases the drag area. So there are two things here that are really at odds with each other. Which one will win? So for D2, which is for the maximum deflection, but also the lowest ride height, we still get an increased drag area. So the negative effect of the tire deformation outweighed the positive effect of the lower ride height. This trend holds true for both the Driv Air car and the Aero SUV car. Now we should also point out that the differences are quite small, only a few counts, which no CFD method these days can even accurately produce anyway. Anyway, in figure 30, we see the drag area breakdown for the various components of the car, and the changes are very minimal, so I don't really think we can conclude anything because it's mostly within the error. In figure 31, we have the same plot, but for the Aero SUV, and I think a similar conclusion can be drawn here where the changes are very small, so I don't think they stand out from a CFD error necessarily. And with that, we come to the end of this podcast. It was really informative, and the takeaway messages are that lowering the ride height is good for the drag area, and as is having less tire deformation. And if you want to learn OpenFOAM so you can do simulations like this or anything else you like, then take our courses in the link below. Again, we have that Christmas special on, which is really good. I think you'll really like it. Anyway, and if you like this episode, hit the like and subscribe buttons, and we'll see you this one. Peace, amigos.